Welcome back, everyone, for another deep dive. This time, we're going to try and unlock the secrets of Gaussian processes.
They're really powerful tools.
They are.
Clear.
But
Yeah.
when you have data sets that are huge GE, things get a little complicated.
Yeah, the calculations get really intense.
They do.
Like if you're trying to model, say, global weather patterns,
Right.
that's a ton of data.
It's overwhelming. And that's where Vecchia approximations come in.
They offer a really clever workaround to that problem.
So we're going to be talking all about Vecchia approximations today. And this deep dive is going to be based on a 2021 paper by Matthias Katzfus and Joseph Guinness.
A general framework for Vecchia approximations of Gaussian processes.
So essentially, Vecchia approximations, I think of them as like...
It's like if you're working on a giant jigsaw puzzle,
Okay.
you wouldn't try to put all the pieces together at once.
Right. Too overwhelming.
You'd break it down into smaller sections.
Right. Manageable chunks.
And Vecchia approximations work in a similar way. They're simplifying these complex calculations by focusing on smaller, more manageable pieces of data.
Okay. So Katzfus and Guinness talk about this problem of quadratic memory and cubic time complexity. What in the world does that even mean?
Well, imagine you're searching through a list, and the longer the list gets,
The longer it takes.
the longer it's going to take.
Right.
Well, with traditional Gaussian processes, as your data set grows, the time and memory that's required to actually do the calculations increases at an even faster rate.
Wow.
It's like that list is growing exponentially.
So Vecchia approximations come in to streamline things.
Exactly. They're strategically choosing which data points are most relevant, kind of like finding the key pieces in that jigsaw puzzle that hold each section together.
Got it. So it makes it more manageable.
Exactly.
And the paper that we're looking at today actually provides like a general framework for understanding these approximations, which is really neat.
Yeah, it's a really elegant framework because it reveals how seemingly different approaches to Gaussian process approximations are actually interconnected. It's like discovering this hidden pattern connecting all these different puzzle-solving techniques.
Oh, cool. So let's talk about those different approaches. Katzfus and Guinness mentioned several types of Vecchia approximations. What are some of the highlights?
Well, one example is the nearest neighbor Gaussian process,
Nearest neighbor.
or NNGP.
NNGP. Got it.
And the idea here is that data points that are closer together are more likely to influence each other.
Makes sense.
So, like if you're trying to predict soil moisture, measurements taken right next to each other
Right.
are probably going to be more similar than those taken miles apart.
Yeah, that's very intuitive.
Exactly.
So by focusing on these nearest neighbors, the NNGP is simplifying calculations while still capturing those relationships.
Exactly.
Cool. What about some of the other approaches?
Another one is called the independent blocks approach.
Independent blocks.
And it's like dividing your puzzle into separate blocks and treating them completely independently.
Okay.
So this can be really simple and fast, but it might miss the bigger picture.
Right. You might miss those connections between the blocks.
Exactly.
Okay, so that's a trade-off there.
Exactly. It's a trade-off between simplicity and accuracy.
Right.
And then there's the multi-resolution approximation, or MRA.
Multi-resolution approximation, MRA.
Right.
Writing all this down.
So imagine you're looking at a map.
Okay.
You can zoom out for a broad overview or zoom in to get the street-level view.
Right.
MRA works in a similar way. It starts with a coarse view of the data, and then it gradually adds in more detail
Interesting.
as needed.
Okay.
This can be really helpful for data sets with really complex patterns.
Multi-scale patterns.
Exactly.
So it sounds like each of these techniques has its own strengths and weaknesses.
Exactly.
And depending on what type of data you're working with, you might choose a different one.
Precisely. And this is where the general framework developed by Katzfus and Guinness becomes so valuable.
Okay.
Because it helps us see how these seemingly different approaches are actually all variations on a common theme.
Uh-huh.
And it provides a way to systematically choose the best approach for a given problem.
That's really helpful. But you know what really caught my eye in this paper is the sparse general Vecchia approach.
Ooh, yeah, SGV.
SGV, tell me more about that.
SGV is really exciting because it strikes a balance between accuracy and computational efficiency.
Okay.
It's like finding that sweet spot in puzzle solving where you're working quickly but not sacrificing the quality of the final picture.
I like that analogy.
Yeah.
But I have to admit, sparsity sounds a little intimidating. Can you explain that in a way that makes sense to someone who's not a math whiz?
Absolutely. Imagine a giant spreadsheet where most of the cells are blank.
Okay.
That's sparsity.
Okay.
And in the world of data analysis, lots of blanks, or zeros, actually make calculations much faster.
Oh, interesting. Okay.
So SGV strategically chooses between using actual observed data and estimated or latent data to create this sparsity and speed things up.
So it's kind of like decluttering your data
Exactly.
for maximum efficiency.
Exactly.
And how does it decide which data to use and which to estimate?
That's a great question. And it brings us to two key choices that Catsfuss and Guinness highlight: ordering and conditioning.
Ordering and conditioning.
So ordering refers to the sequence in which you analyze your data points.
Okay.
And this can actually make a big difference in capturing patterns, especially in spatial data.
So like imagine organizing your puzzle pieces based on their row and column number versus just scattering them randomly.
Exactly. The organized approach is likely to be much more efficient.
Makes sense. Okay, so what about conditioning?
Conditioning is about choosing specific data points to be kind of reference points for your predictions. Think of it like selecting a few key pieces from different sections of your puzzle to guide your assembly.
Gotcha.
Catsfuss and Guinness suggest several approaches for conditioning, including focusing on the nearest neighbors of the data point that you're trying to predict.
So it's all about making these smart choices to simplify the complex calculations without sacrificing accuracy.
Exactly.
Now, to really see how well these choices work in practice, Catsfuss and Guinness, they put SGV to the test
It did.
in order to perform.
Drumroll, please.
Yeah.
SGV consistently outperformed other methods in terms of accuracy while remaining computationally manageable, even with data sets containing hundreds of thousands of data points.
Wow. That's really impressive. So it lives up to its promise.
It does, and what's even more remarkable is that SGV achieved this performance while maintaining a computational speed that scales linearly with the size of the data set.
Hold on. Remind me what linear scaling means again.
It means that the computation time increases proportionally to the size of the data set. So if you double your data, the computation time roughly doubles as well.
Okay, got it.
Which is a huge improvement over traditional Gaussian processes, where the computation time can just skyrocket as your data set grows.
Right.
It gets really intense.
So SGV is like this super efficient engine that can handle those massive data sets.
Yeah. But you did bring up a good point earlier. You remember how you mentioned latent Vecchia scaling quadratically?
Oh, yeah.
So latent Vecchia, which is used in the nearest neighbor Gaussian process, can actually offer even better accuracy than SGV,
Okay.
but at a cost.
Okay.
Remember how SGV balances using observed and latent data to achieve that sparsity?
Uh-huh.
Well, latent Vecchia relies entirely on latent data.
Okay.
And that can result in much denser calculations, meaning it can be slower.
So it's like choosing between a super fast sports car that's really fuel efficient or like a luxury sedan that like guzzles gas but offers a really smooth ride.
I love that analogy. Latent Vecchia might be great for smaller data sets where accuracy is paramount,
Right.
but it becomes computationally impractical as the data size grows. So SGV offers more of a balanced approach.
So it seems like Catsfuss and Guinness have given us this powerful new tool
Yeah, you have.
for tackling large-scale data analysis problems with Gaussian processes. They haven't just introduced a new method, they provided a whole framework
A whole new way of thinking about.
for understanding these approximations.
Exactly.
That's super helpful.
And this is just the tip of the iceberg.
There's more.
Catsfuss and his colleagues have continued to build on this framework.
Wow.
They've extended it to Gaussian process predictions and explored its applications in various fields.
Wow. So we've got a lot more to talk about.
We do.
But before we get into all of that, I think it's time for a quick break.
Sounds good. So before the break, we were talking about how Catsfuss and his colleagues have extended this framework to Gaussian process predictions.
Right, which just sounds incredible to me. Like we could predict the future with Gaussian processes.
Well, not exactly predicting the future, but it's about making predictions at new locations or time points where we don't have data.
Okay, so extrapolating in a way.
Exactly.
And to do this effectively, we need to think carefully about those key choices, ordering and conditioning.
Right. We talked about those before the break. Ordering is like deciding the route you take through your data.
Yeah, like planning a road trip.
And conditioning is like choosing the landmarks you want to visit along the way.
Okay, yeah, I like that analogy.
So can you walk me through this a bit more? Like for ordering, I get how it's important for time series, going from past to present. But what about spatial data? What does ordering look like in that context?
That's a great question. In two or more dimensions, like on a map, we need to think about how to visit each data point in a way that makes sense.
Okay.
Catsfus and Guinness explore different ordering schemes, including what's called coordinate-wise ordering,
Coordinate-wise.
which is kind of like arranging your puzzle pieces based on their row and column numbers.
So very systematic. Right. But they also introduce a more sophisticated approach called maximum minimum distance ordering.
Maximum minimum distance. That sounds a little complicated.
It's actually quite intuitive. Imagine you're placing points on a map. With maximum minimum distance ordering, you always try to place the next point as far away as possible from the points that you've already placed.
Oh, so you're spreading things out to cover the whole area.
Exactly.
Okay, that makes sense.
And this helps ensure that each new data point you analyze is bringing in unique information, and it helps capture those spatial dependencies more effectively.
So we've covered ordering. Now what about conditioning? We talked about choosing reference points for our predictions.
Right. And one common approach is, again, that nearest neighbor conditioning,
Nearest neighbor, yeah.
where you focus on the data points that are closest to the one you're trying to predict.
Okay,
It's like looking at the pieces that immediately surround the one you're trying to fit in your puzzle.
it makes sense.
It's a very local approach.
But are there times when we might want to look beyond just the nearest neighbors?
Absolutely. Catsfuss and Guinness point out that for very smooth data sets, where the values are changing gradually over space or time, conditioning on a fixed set of reference points can be more effective.
So,
They call this the same conditioning set, or SCS approach.
same conditioning set, SCS.
Got it. So instead of just looking at the immediate neighbors, you're choosing a few key pieces from different sections of the puzzle to guide you.
I like that. So it seems like there are a lot of factors to consider when choosing the best ordering and conditioning strategies.
You're right. The optimal choice will depend on the specific characteristics of your data.
Okay.
Things like the dimensionality, how smooth the underlying process is, and whether there's a lot of noise in the data.
So it's not a one-size-fits-all solution.
Exactly.
You have to tailor it.
You have to think carefully about the problem you're trying to solve and make informed choices about these parameters. And to help guide us in making those choices, Catsfuss and Guinness actually conducted some really interesting numerical studies to compare different SGV strategies.
Oh, so they put these ideas to the test.
They did. And one of their key findings was that maximum minimum distance ordering often led to significant improvements over that coordinate-wise ordering, especially for data sets with a low signal-to-noise ratio.
Low signal-to-noise ratio. Can you refresh my memory on what that means?
Yeah, imagine trying to listen to a radio show and there's a ton of static.
Okay, yeah.
So the signal is really weak
Right.
compared to all the noise.
It's hard to hear.
In data analysis, this means that the underlying patterns in the data are kind of obscured by all these random fluctuations.
Gotcha. So in those cases, choosing the right ordering strategy is super important.
It's crucial. Their studies also highlight the importance of considering the smoothness of the underlying process when choosing a conditioning strategy.
Smoothness, okay.
So for very smooth data sets, the SCS approach that same conditioning set often outperformed nearest neighbor conditioning.
Okay.
But for less smooth data sets, the opposite was true.
So again, the right tool for the job.
Exactly. It all comes down to understanding the properties of your data and making informed choices.
Well, Catsfuss and Guinness seem to have done a great job of giving us a roadmap to navigate these complexities.
They really have, and their work has generated a lot of excitement in the field.
That's awesome. But I have to admit, I'm still a little fuzzy on how these Vecchia approximations actually work on, like, a technical level. Can we break that down a bit more?
Of course. Remember how we talked about sparsity being key to the efficiency of SGV?
Yeah, the whole lots of zeros makes things easier idea.
Right. Well, that sparsity is achieved by strategically choosing which data points to condition on, and then representing the relationships between data points in what's called a sparse matrix.
Okay, wait. Sparse matrix. I'm getting flashbacks to linear algebra class.
Don't worry, it's not as scary as it sounds.
Okay, good.
Remember that giant spreadsheet we talked about?
Yeah.
So a matrix is basically a table of numbers.
Yeah.
And a sparse matrix is one where most of those numbers are zeros.
Okay, so like that decluttered spreadsheet.
Exactly. And in the context of Vecchia approximations, that sparsity translates to much faster and more efficient calculations.
So instead of having to crunch numbers in every single cell of that spreadsheet,
Exactly.
we're just focusing on the cells that really matter.
Exactly. And that's how SGV achieves its remarkable computational efficiency.
Wow, that's pretty clever. But how does it actually choose which cells to focus on?
That's where those choices about ordering and conditioning come into play.
Right, right.
Ordering determines the sequence in which we analyze the data points,
Uh-huh.
and conditioning determines which data points we're going to use as those reference points for our predictions.
Got it. Okay, I'm starting to see the connections here.
Good. Now, to represent the relationships between these strategically chosen data points, we use a special type of sparse matrix called a Cholesky factor.
A Cholesky factor. That sounds pretty technical.
It is a bit technical,
Okay.
but the main takeaway is that the Cholesky factor allows us to very efficiently compute the inverse of what's called the covariance matrix.
Covariance matrix. That's ringing a bell, but remind me what that is.
The covariance matrix basically captures the relationships between all the data points in our data set. It tells us how much one data point is likely to vary with another data point.
Okay, so if two data points have a high covariance, they're likely to move in the same direction.
Exactly.
And if they have a low covariance, they're more independent.
Precisely. Now, in traditional Gaussian processes, computing the inverse of this covariance matrix can be incredibly computationally expensive,
Yeah.
especially for large data sets.
And that's where that whole quadratic memory and cubic time complexity comes in.
Exactly. It can become a real bottleneck.
A real problem.
But Vecchia approximations, and particularly SGV, offer a clever workaround by exploiting the sparsity of this Cholesky factor.
So instead of trying to invert that whole massive covariance matrix, we're just focusing on the parts that are relevant.
Exactly. And this allows us to perform those Gaussian process calculations much more efficiently, even for data sets with hundreds of thousands or even millions of data points.
That's incredible. It's like finding a shortcut through a dense forest.
That's a great analogy. And that's really the beauty of Vecchia approximations.
So they're like a superhighway for data analysis.
Exactly. They unlock the power of Gaussian processes for large-scale data analysis.
And open up a world of possibilities.
A world of possibilities, exactly.
Okay, so we've talked about how awesome these Vecchia approximations are for modeling data. But you mentioned before the break that Catsfuss and Guinness also extended this framework to address Gaussian process predictions.
Yes. So while SGV is incredibly efficient for modeling data, it doesn't directly address the challenge of making predictions at new locations or time points.
Right, so we can model the data we have really well.
Yeah.
But what about predicting what might happen in the future? Or at places where we don't have data?
Precisely. And that's where their 2020 paper comes in.
Okay.
In this work, they extend the Vecchia framework to specifically address Gaussian process predictions and introduce a method called multi-resolution approximation for predictions.
Multi-resolution approximation for predictions, or MRAP.
MRP, exactly.
Okay, I'm getting all the acronyms down. So it's like MRA, but
Well-
specifically designed for making predictions.
Precisely. MRAP builds upon that multi-resolution idea where we start with a coarse view and gradually add detail.
Okay.
But in this case, it's all about efficiently computing predictions at new locations or time points while still leveraging the sparsity of Vecchia approximations.
So it's like having this high-resolution map that lets you zoom in on any location and get a detailed prediction, even if you don't have data at that specific spot.
That's a fantastic way to think about it.
That's pretty amazing. It's like getting into science fiction territory here.
It is pretty remarkable. It highlights how Catsfuss and his colleagues are really pushing the boundaries. But, I think it's time we address the elephant in the room.
Okay. Elephant in the room. What do you mean?
Well, we've been talking about all the amazing benefits of Vecchia approximations. But like any tool, they also have some limitations.
Right. Nothing's perfect.
Exactly. So one important consideration is the choice of those Vecchia approximation parameters.
Oh,
Those choices we make about ordering and conditioning.
Those seem pretty crucial.
They are. And while Catsfuss and Guinness provide some really excellent guidance, finding the optimal settings for a given problem can still require some experimentation and fine-tuning.
So it's not always a plug-and-play solution.
Not always. You might have to try different things to find that sweet spot between accuracy and computational efficiency.
Okay, that makes sense. What other limitations should we be aware of?
Well, another thing to consider is the type of data that we're working with. Vecchia approximations work best for data that exhibits some degree of smoothness or spatial correlation.
Smoothness. So data where the values change gradually rather than jumping all over the place.
Exactly. If your data is super erratic and doesn't show any clear patterns, Vecchia approximations might not be as effective.
So we need to know our data.
Absolutely. It's crucial to understand the characteristics of your data before diving into these methods.
Okay, good advice.
Yeah.
So To wrap things up, what are some of the key takeaways you want listeners to remember about Vecchia approximations?
Well, first and foremost, I want them to appreciate the elegance and power of Catsfuss and Guinness's general framework. It's not just about introducing a new method.
Right.
It's about providing this unified understanding of how all these different Gaussian process approximations are connected.
Like a whole new way of looking at it.
Exactly. And second, I want listeners to really grasp the importance of SGV.
That's sparse general Vecchi.
As a practical and efficient tool for handling large-scale data analysis problems with Gaussian processes.
Yeah, it's a game changer.
It really is. It opens up a world of possibilities for researchers and practitioners. And lastly, it's important to remember that Vecchia approximations aren't a silver bullet.
Right, they're not magic.
Exactly. They have their limitations, and choosing the right approach requires careful thought about the problem you're trying to solve and the nature of your data.
Okay, that's a good point. So, to leave our listeners with something to ponder, what's that question you wanted to pose?
So we've talked about how Vecchia approximations make What if we could go even further? What if we could make these approximations even more efficient?
Oh, okay, so where are the next breakthroughs waiting to happen?
Well, one area that's ripe for exploration is how we choose those key parameters, the ordering and the conditioning.
Right.
Right now, it often involves some trial and error. But what if we could develop algorithms that automatically find the best choices based on the data?
That would be amazing. It would make these techniques so much easier to use, even for people who aren't like experts in Gaussian processes.
Exactly. And think about the potential for real-time applications.
Oh, yeah.
If we can make these approximations even faster, we could analyze data as it's streaming in from sensors, from financial markets, from all sorts of sources.
So it'd be like having a crystal ball
Yeah.
that's constantly updating.
Right.
You could make decisions and predictions on the fly based on the very latest information.
Exactly. And another area for innovation is extending these techniques to even more complex types of data. What about data that's not just spatial or temporal, but has a network structure?
Okay.
Like social networks, transportation networks.
Yeah.
There's a whole world of possibilities out there.
So we're not just talking about points on a map or events in time. We're talking about relationships between things.
Precisely. And imagine the insights we could gain by applying Gaussian processes and Vecchia approximations to these complex networks. We could understand how information spreads, how diseases propagate, how traffic flows through a city.
That's incredible. Like the potential impact on everything from public health to urban planning is huge.
Absolutely. It really highlights the transformative potential of these techniques.
But this whole conversation has got me wondering, why aren't more people talking about Vecchia approximations?
That's a great question.
Like, they seem like such powerful tools. Why isn't everyone using them?
Well, honestly, it's probably just a matter of time. These techniques are still relatively new, but as more people become aware of their benefits, I think we'll see an explosion of applications across all sorts of fields.
It's like we're on the cusp of a revolution in data analysis.
It really does feel that way.
And thanks to this deep dive, our listeners are going to be ahead of the curve. They'll be the ones who recognize those opportunities where Vecchia approximations can really make a difference.
Exactly. And remember, Catsfuss and his colleagues have laid a strong foundation with their work on SGV and MRP. It's up to us to build on these ideas and push the boundaries even further.
Well, I don't know about you, but I'm feeling inspired. I'm ready to go out there and find some massive data sets to conquer.
That's the spirit. And remember, with the power of Vecchia approximations, even the most daunting data challenges can be overcome.
So folks, that wraps up our deep dive into the world of Vecchia approximations for Gaussian processes. We hope you've enjoyed this journey into the realm of efficient and accurate modeling with massive data sets. And who knows, maybe you'll be the one to make the next big breakthrough in this exciting field.
Until next time, keep exploring, keep learning, and keep pushing the boundaries of what's possible with data.